In this video, we are going to discuss the implicit function theorem. So the implicit function theorem, which I'll abbreviate IFT, is actually the theoretical basis for the technique of implicit differentiation, which you probably learned in calculus. And Munkres, at the beginning of section 9, has a really good explanation of how these two ideas are related. We'll also do an example at the end of this video, which should illustrate this for you. Before we get into the statement of the theorem, I need to make a bit of notation. So if I have a function from Rn cross Rm to Rm, then its differential can be written as the concatenation of two matrices, d sub x of f and d sub y of f. So this matrix has n columns. This matrix is a square matrix. It has m columns. So I sort of think of d sub x as the sort of partial derivatives in terms of x, and the d sub y matrix as the partial derivatives in terms of y. So the statement of the theorem is as follows. If U is a neighborhood of a point x naught in Rn, V is a neighborhood of y naught in Rm, f is a function from U cross V to Rm, it's differentiable, and moreover, d sub y of f at the point x naught, y naught is invertible. And let me make the notation f of x naught, y naught is equal to z naught. Then we can conclude that the preimage, essentially the preimage of z naught under f is the graph of a function. But we'll say that there is a function f from Rn to Rm with f of x naught equaling y naught and big F of x, f of x equaling z naught if x is in W, which is some neighborhood of x, and moreover f is differentiable, and it's unique. So before I prove the theorem, I'm going to draw a cartoon. So here are, in this cartoon, the x-axis is the Rn directions, and the y-axis is the Rm directions. And so f would be defined on this block, and it would send that block to Rm. And there's a point z naught, which is the image of the dot, which is x naught, y naught on the left-hand side. And if I were to look at the preimage of z naught, so now I'll draw z naught in red, and take all the points in U cross V, which f sends to z naught. Maybe there's like a, maybe f is kind of weird and it has like, so most of the time I've drawn this as sort of a one-dimensional thing, but maybe there's like a blob, f might not be, super differentiable or nice, not necessarily not differentiable, but not super nice away from x naught, y naught. But since we're assuming that d sub y of f is invertible at x naught, y naught, what this tells me is if I zoom in close enough to the point x naught, y naught, there's some neighborhood, maybe a smaller neighborhood W of x naught, on which I can actually draw the level set of z naught as the graph of a function f. So that's what we're going to be proving. And we'll do some examples that will really drive this point home. Okay, so we're going to use the implicit function theorem to prove this theorem. So let's construct an auxiliary function. H of xy is x, f of xy. Now, if I take dh is going to be the n by n identity matrix in the top left corner. And then there'll be a bunch of zeros. So I'm writing it as a block matrix. Not all these blocks are going to be the same size. And then the bottom sort of row, quote unquote row, is just df. And you can show using the definition of the determinant that the determinant of dh at the point x naught, y naught is just equal to the determinant of, sorry, not f, d sub yf at x naught, y naught, which we're assuming is non-zero. And this is just because if you have any permutation in your computation of the determinant of dh, which includes any entries from this part, then that contribution from those terms will all just be zero. So what you're going to end up getting is all your permutations will have to include just the diagonal in through this identity, and then some permutation from the d sub yf, and then summing all over all those permutations just literally gives you the determinant of d sub yf. Okay, so this tells us that I can use the inverse function theorem on h, which gives me an inverse function which is differentiable. And j is, moreover, notice that because j of xz is equal to, so sorry, not j of xz, j of x, f of x, y has to equal just xy. J also has to send the first n coordinates to the first n coordinates. So this implies that there is some function g such that j of x z in general is just equal to x g of x z. So all this is saying is that j doesn't touch the first n coordinates, essentially. And this uniquely defines g, right, because j is uniquely defined by being the inverse of h. So now I need to define my function f. So let's take j of x z naught. This is going to be x g of x z naught. And if I take h of both sides, well, j is h inverse, so this is just x z naught. And by the definition of h, this is h x comma f of x g of x z naught. There should be 3. And now if I just take the second component, this tells me that z naught is f of x g of x z naught. So what this tells me is that every point of the form x comma x g of x z naught is an element of the preimage of z. So this is exactly what I wanted to, how I wanted to define my function f. So I want to define f of x to equal g of x comma z naught. And so all this equation tells me is that pairs x comma f of x are elements of the preimage of z naught, but actually because h is invertible, j is actually a function. So this is all that. So if anything is in the preimage of x of z naught, it has to be of the form j of x z naught. So that means it has to be of the form x f of x. And finally, so this tells me essentially by the argument I just said, this defines f uniquely. And f is differentiable, sort of because j is, and f is derived from j. That might not be super satisfying because it doesn't tell you how to compute the derivative of f. So what we'll do next is compute the derivative. So this theorem is Munkres theorem, theorem 9.1. It doesn't really have a name. So the theorem says that d sub f at a point x is minus d sub y of f at x, f of x. Actually, I did not give myself enough space for this. Let's move it down here. Inverse multiplied by d sub x of f at the point x, f of x. So this proof is just a computation. So I'm going to define another auxiliary function, k of x is equal to f x little f of x. And this function is constant. So I can take dk at x, and that's just has to be the zero matrix. And now by the chain rule, I get that the derivative of the right-hand side is df at x f of x, and then d of the function which sends x to x f of x. So when I actually write that down as a matrix, it's going to be the n by n identity matrix and then df at x. Okay, and then now I can, so this equation tells me that 0 is equal to this stuff, and I'm going to rewrite df as d xf at x f of x, dyf at x f of x, multiplied by this matrix. And then if I do the matrix multiplication, you can see that I'll just literally get the exact thing that I wanted. So I'll get dx f at x f of x plus dyf at x f of x times df at x is equal to 0. And this is the proof. Notice that this, if you rearrange, you get this equation. Notice that this goal equation here only makes sense, right, if d sub y of f is invertible. So it only makes sense in this neighborhood w, close to x naught. So finally, let's do an example. So in this example, f of x, y, so here n is just going to equal m, is going to equal 1, the simplest possible case. F of x, y is going to be x squared plus y squared. And let's choose x naught, y naught to be the point 1, 2, and z naught will now be 5. So in this case, you're probably familiar with this. This is the circle of radius root 5, and the point 1, 2 will be right about there. And f is going to send, so f actually sends all of Rn to, all of R2 to R, right? So f is defined on all of R2. So this, you know what I can do? I can turn this, not going to do any fancy iPad tricks. I'll just color over this red. This red is the level set of the point, so here's my R, the level set of the point 5, right? Which is my z naught. So I can't, it's pretty clear that this is not the graph of a function everywhere. But if I zoom in close enough, I didn't draw this great, but if I take a small enough neighborhood, then the level set actually is the graph of a function. So in this case, f, you can just solve this. F is equal to the square root of 5 minus x squared. And if I want to compute its derivative, f prime of x is, let's see, it'll be 1/2 times 5 minus x squared to the negative 1/2 times negative 2x. So this should all work out to be negative x divided by root 5 minus x squared. And in particular, f prime at 1 is negative 1 over 2, because 5 minus 1 is just 4. But now, if I go to my formula, so I have, this should tell me that f prime at 1 should be equal to negative d sub y of f inverse times d sub x of f. So what I need to do is compute df. df takes should take two numbers and send them to 1, so it should be a a row matrix. And if I compute it, the derivative of f is just going to be 2x, 2y. So d sub x is always just the matrix 2x. D sub y is just 2y. And so if I compute what df at the point 1 is, it's going to be negative 2 times 2 inverse times dx, which is going to be 2 times 1. So this will be negative 1/2 as well. But if I chose x naught, y naught to be root 5, 0, in this case, dy of f is the 0 matrix, and I can't use the implicit function theorem. And that kind of makes sense, because if I were to look near this point here, there's no neighborhood on which, so let's zoom in maybe. There's no neighborhood of x on which I can actually draw the graph of a function and get the level set of 5.